Hello. Here we'll discuss the Newton's binomial formula. Which says something about the power of a sum. Let's take two things, A and B, and then compute the nth power of their sum. Well, what should we expect as a result? That is, by the definition of nth power, is the product of n copies of a plus b. And we can use arithmetic, which allows us to distribute summands through this product. So collecting one summand from each of the factors, we will be seeing some products of copies of A and copies of B. The total number of factors in these products will have to be n. So say if we have I copies of B, then n minus I copies of A have to be around that. The total power has to be n because we only have we have n factors. So that will be summands in our sum, and we can think of the lowest parameter I. So I is the only parameter we have in describing these monomials. The lowest value I is 0, and of course it is possible to get no b's. Just take A throughout the product from any of the factors. So I can start with 0 and can end with the other extreme when we don't have a's in the product, in the monomial. We'll just choose b's, and that will be the end value of the running index in the sum. And let's now just denote the coefficients with which each of those monomials appear by some notation. So this is the binomial coefficient notation. And the task of this little discussion is to determine them to some extent, to see how can we compute them and how can we say something about them quickly. So the beginning of this story, of course, is when n is equal to 1, or rather n equals 0. So that is 0th power, which by agreement is to be 1. And on the other side, we have the product of the 0th power of A and the 0th power of B, and it comes with coefficient, which are both 1, comes with coefficient according to this notation C0, 0. So that is determined in 0, 0 binomial coefficient to be 1. That is rather trivial. Let's look at the next one, which is also trivial. So we just have A plus B, and the coefficients are 1. So these coefficients have names 1, 0 for the first, and 1, 1 for the second, and they're both 1. Since we're computing all powers, it is reasonable to use induction. So let's just try to apply induction to this base, and assuming that we know something about these coefficients, this expression, derive some information for the next power and the next layer of binomial coefficients. So for that induction step, I will write the next power as a product of A plus B and the previous power, and I know about the previous power, and I'll just spell this compact sum notation out in say a lone sum. So I'll have 0, 0, that is the coefficient for A to the power n no b's, and I have sorry, not 0, 0, but n 0. I have n1 for A, n minus 1 copy of B, and all the way down to nn, which will be just the coefficient for B to the n. So that is what I need to multiply with another copy of A plus B. And I will do it separately for A, multiplying this lone sum with A, and then multiplying it with B and taking the sum. So when I multiply with A, each of those segments, I will have the coefficients don't change, it's just the powers of a will change in each of the monomials. I'll have the same coefficient now for an, because it was a n minus 1 with extra copy of a will be a to the n times b, and goes all the way down to this term. So that is what happens when we multiply the lone sum with a. Let's see what the product with b will be. I'll write it just under this, and I will use a shift because I want to align the monomials in the product. So the first monomial in the product with b will be a n b, so just below what I had, similar monomial I had above. But the coefficient now is n0, coefficients don't change, and I will skip this, but I will spell out one before this. Well, actually, yeah, one before this, when I have n minus 1, so I had a product of a and b to the n minus 1, but then it becomes b to the n after multiplying with b, and then the very last is the product of this with b, which will be b to the n plus 1. So that is to be summed, and you could see what happens. Well, that is to be summed and compared with the template, which says that now we have n plus 1th layer. This is a 0 coefficient of a n plus 1. This is the sum of those is the first coefficient, n plus 1. It's a coefficient for a n times b. And yeah, I'll just stop here all the way down to this, which is n plus 1, n plus 1, coefficient of n plus 1. So we have the recursion. We can see that the extreme coefficients, the 0th coefficient on the next layer doesn't change, it's still the same as this coefficient on the nth, for the nth power, which of course is equal to 1, and the same for the last. So the last coefficient on the level of n plus 1 is equal to the last coefficient on the level of n, and it's also 1. In the middle something interesting happens, so if we just look at anything between 1 and n, we will have the sum of 2, and there will be, for 1 there will be 1 in the previous, for 2 there will be 2 in the previous, and we can just write it in generic form like that. So that is for any I in between 1 and n including. Another is a recursion, which is already good enough to iteratively compute the binomial coefficients. So goes back to Pascal. The form of this computation arranged in the triangle, so it is called Pascal's triangle. And you basically list all the binomial coefficients in the row. So the first row is just the level 0, 0's power, only one coefficient, which is 1. Below, with a shift to the left, are the two coefficients, binomial coefficients for the first degree. And then this recursion says that the extreme coefficients are going to be 1, so just keep continuing with these 1s. All bulk binomial coefficients are obtained from the previous level by taking the sum of two things just above. So here we have the 1 and 1 above the coefficient, which has to be their sum, which is then going to be 2. Here the coefficient is going to be the sum of 1 and 2, going to be 3. And again for this position, 2 above, 2 and 1, and their sum is 3. Then the next layer is going to give us 4, 6, and 4. And the next after is going to give us 5, 10, 10 again, and 5, and one after is going to be 6, and 15, and 20, and then repeating again. So you can see that the coefficients in each row are symmetric about the middle of this triangle. So I really don't need to copy it all the way, just skipping one. And I don't have much space to continue, but you could see what happens. So here's the separator. Let's finish with the argument in favor of a more compact expression for the binomial coefficient. Yeah, that is an effective way of computing them, but it's hard to see what is on the level number 31. So here's a formula which is going to be answering, to some extent, this question. So if I want to compute any of those binomial coefficients, what I can do is to take the factorial of n and divide by the product of the factorial of I and the factorial of n minus I. By the definition, these are counting coefficients, these are natural numbers, so this looks like a rational function, but it is a natural number because this denominator divides in the factorial neatly. So that's what we're going to prove using this recursion. Again, the base is we will be proving by induction by n, and the base is say this case or this case, and they both can be checked explicitly. So when this is 1 or this is 0, 1, we have the answer. Then we can check the extreme cases explicitly. So if we have arbitrary n but we have 0 or n here, again the answer should be as predicted, should be 1. So all we need to check is the bulk, this bulk of the triangle, and that can be done by just verifying that the formula produces the answer on the next level with this formula. So let's see how it works. So we need to see that this coefficient is going to work according to the prediction, and the prediction says that it should be n plus 1 factorial, so we just replace n by n plus 1, divided by I factorial, so the factorial of this down index, and then whatever n is, which is n plus 1 now, we have to subtract this I from it and take the factorial. So that's a prediction we need to verify. So let's see what we have. So we have this sum of two binomial coefficients on the previous level, which I now, assuming my induction assumption, spell out as these ratios of factorials. The other one will be for the low index being I minus 1. So I have I minus 1 factorial n minus I minus 1, so it is n minus I plus 1 factorial. Well, just remember what factorials are, so that's what we're proving, but here just before that, factorials are products of all the numbers in the row up to the given one. And they obviously have this property that if we take the next factorial, that will be the factorial before times the number. So that is just the basic property coming from the definition. That's what we can use in here, because what the next arithmetic step we should do obviously is to make a common denominator to compare with the expected answer. So before making the common denominator, let's make this look nicer. So we have I minus 1 factorial times I instead of this, and we keep the second factorial unchanged. So my bar is still on. So here I keep I minus 1 factorial unchanged, and then break this factorial into n minus 1, into n minus I factorial, times n minus I plus 1. And again, the numerator is n factorial. So that is to be merged with this. So that is now we can see common things. I minus 1 factorial in both denominators, n minus I factorial in both denominators. So we see what we need to multiply each of the numerators to merge to the common denominator. So let's first list this common denominator. We'll have I minus 1 factorial, and I, then n minus I factorial, then n minus I plus 1. And then here we are missing n minus I plus 1. So again, n factorial I can factor out of the sum. The first summand will be n minus I plus 1. And the second will be whatever missing in the denominator, which is I. So that, when simplified, now I'm going to collapse these factorials again into I factorial and n minus I plus 1 factorial. Upstairs I have n factorial, and this sum is nothing but n plus 1. So that, combined together, just gives me what I am expecting to see. And that is my induction step. That is proving the formula here for all n's. So assuming it worked for n, I proved it for n plus 1. See you soon with an application of this binomial coefficient formula.